we will be talking about the composition of two functions, but before we do this, I would just like to look at an example. What we're going to do is start with two functions, and then we're going to make a new function out of those two by applying one function followed by another one. So let's just try with our example. So we say f is the square function. So here f is the square function, so in that case it's there and there. And then my other function g is just a function that multiplies by 3, which is there and there. So we just want to know what we get. So f is a square function, so if I start with x, I'm going to get x squared. I then apply the function which multiplies by 3, and I get 3x squared. Now if I do g followed by f, now this time I'm applying g first. G multiplies by 3, so I'm going to get 3x, followed by f. F is the function which squares the input, so in that case the input of f is 3x, so we're going to be squaring 3x. What we'll be getting is 3x squared, which is 9x squared. So be careful. We can already see on this example that if you do f followed by g or g followed by f, you don't get the same thing. Now we invented a notation that really says you should do a function followed by another one. Here it is. If you have two functions, you can make a new function called f composed with g, and you write it f, and then you have this little circle. So this is f composed with g of f, and the way you read that and what it means is really f of g of x. And if you read it this way, f of g of x, you will know exactly what to do. Putting some emphasis on this because since we always read from left to right, since we see f before we see g, it would be very natural to apply f first. But if you say f of g of x, you will see that you need to find g of x first and then apply f. This is why I've represented here. F composed with g really says apply g, and when you're done, apply f. So in your head, read f of g of x. Okay, now let's see if you got that. Which function did we apply here? Well, it was really, we applied f first and then g. So this is g of f of x. Whereas the second one, we applied f. So that's f of g of x. So the function we have in the first case is going to be g composed with f, and in the second case, f composed with g. Let's get a little bit of practice. So first we said when we see this, we read the little o, if you'd like, the little circle as of. So that's f of g of 3. And let's write this. I'm going to be using the exact same notations and color I had on the other one. F of g of 3. And initially, especially, go slowly. It's really f of. And now you just need to find out what g of 3 is. Well, g is defined here. So g of an input is the input minus 1. So g of 3 is 3 minus 1. So really what we're finding here is f of 2. Now f of 2, what f does, f squares the input. So we just need to square the input and we get 2 squared, which is 4. This first question was a kind of warm-up to make sure you understood the notation, and you could do this in the general case. Now, f of g of x. That's again f of, inside you will have g of x, and then you just write what g of x is. G of x is x minus 1. If you look at the definition you have for f, f is the function which squares the input. If the input is x minus 1, well, f will square x minus 1. And this is what you get. F composed with g of x is x minus 1 squared. Let's try it now to do g of f of x. I'm going to use the same colors by putting the outside function in red and the inside function in blue. G of f of x. just reading what that means. So it's going to be g of, and I just copy what f of x is. F of x is x squared. Now what does my function g does? G is the function that subtracts 1 from the input. So my input is x squared and I subtract 1. And please note that I get something totally different. For instance, if you put in x equal to 0 in this one, you will get 1. And if you put x equal to 0 in this one, you get negative 1. So what do you notice? F composed with g and g composed with f are not necessarily equal. Sometimes they will be equal, in most cases they will not be. So just compose in the order that you think make the calculations easier. Follow what it says and read in your head f of g of x or g of f of x, depending on what the question is. Let's apply these to some of the functions we know. So first I'm going to ignore this first part here, we'll see later on what we do there. Here this is exponential of ln of x, which I could write exponential of ln of x. And we already said that exponential and ln undo each other. So I'm back to x. Same thing here, that's ln of exponential of x. And since they're inverse function, they undo each other. Now really, the first part of the question, now let's go back to that, is when can we say so? Well, this is true as long as the things make sense. So here, since there is an x inside ln, we know that x needs to be positive, otherwise ln of x just doesn't exist. ln is defined only for positive numbers, so x needs to be positive. After that, we won't have any problem, because you can put absolutely anything inside an exponential. Let's look at the second one. So let's say we start with any real number. Exponential of anything is always positive, always. So then, when you apply ln, you won't have a problem. So that means this can be any number, and the fancy way of writing that at university level is to say x is an element of the set of real numbers. So really it means it can be any number. So it's not too bad to see when it's true, just look when it makes sense. So if you look at what we did, we started from, we composed two functions, applied that to x, and got back to the starting point. Composed a function, applied that to x, got back to the starting point. Why did this happen? Well, we know exactly why it happened. It happened because these functions are inverse of each other. And that's exactly what the question is asking, with them more generally. So what we're going to say is, if you have a function, and you compose with its inverse, and you apply this to something, you get back where you were. Now, if you apply the function first, in that case it's the function first, yes, because it's f inverse of f of x, you get back, usually it's written with bracket, let me use the bracket, you get back to x. Okay, so this is, the example we have is just a special case of inverse function, and that's the general case where we take any inverse function. And same thing for which values of x? Well, for the ones for which it makes sense. This one really is f inverse of f of x. So we need to be able to calculate f of x. So x is in the domain of f. Same thing for this one, Sx to be in the domain of f inverse. But the domain of f inverse is the same as the range of f. In this video, we've learned about the composition of two functions. That's when you apply one function followed by another one. We also learned about the notation we use to describe this, that was the little circle. And really, one of the most important part is we learn to think about it the right way by saying in our head, that's f of g of x, which will prevent mistakes. And then we realized that that was a language that could be very useful to express the idea that f and f inverse are actually inverse of each other. Thanks for listening to this video.